All right, so it's 11:30, so let's begin. Thanks for coming to this talk, Finding Training Inefficiencies with CentML DeepView. So let's begin with this very obligatory slide on the exponential increase of model sizes. So on the y-axis is the training compute requirement. So this is the number of floating point operations to train the model. And on the x-axis is sort of time, right? And notice how the y-axis is a log scale. So what a line means here is the size of these models are growing exponentially over time. And we can already see some familiar models such as GPT-3, but they're quickly eclipsed by newer models that are introduced. And nowadays we have seen much larger models such as GPT-4. And this sort of increase of model sizes not only is true in sort of the largest state-of-the-art models, but also the models that we deploy day to day. And training these models can be very computationally expensive. So compute doesn't come cheap, whether if it's in a cloud such as AWS or on premise. And this cost of training the model is typically dominated by the GPU. And especially for large models, you're going to be spending a lot of your funds on getting like GPU instances to do the training. And let's consider large language models as sort of an example here. So as reported, a GPT-3 cost $4.6 million per training run. And GPT-4, as it has a lot more parameters, it takes around $100 million. And with this sort of growing trend, we expect the cost of training to also continue growing. And it's important to note that this cost that you see here, it doesn't only come from the final training run of the model as you develop the final sort of version, but also during development. People do stuff like hyperparameter tuning or essentially you search for the best model during development, and you have a potentially large pool of configurations that you want to test to find the best configuration. And apart from cost, time and cost, these computations also incur a large large amount of emissions, and this is fundamentally due to the fact that model sizes are growing exponentially, but hardware efficiency doesn't. And on this one, you see the cost of training GPT-3 is roughly equivalent of the lifetimes of 7 average sort of gas cars. And it's important to note that, again, we're looking at some cutting edge models, well, at least by then they're cutting edge. The same sort of principle applies to the models that we train day to day that we deploy in our pipelines. So in addition to training the models, development also incurs a lot of this emissions. So is this problem inevitable? And to answer that question, the main metric that we're going to use is called GPU utilization. And in simple terms, so it describes how much of the time the GPU is spending doing useful work. So your GPU is sort of powered on all the time, attached to your instance, and whether it's doing anything, you're sort of getting charged, and you're getting charged for the instance, and it also consumes a sort of a baseline amount of energy. So you sort of want to make the best use of the GPUs you have. So let's look at 2 examples. So typically, you have a CPU and a GPU on your machine, and the CPU would perform some operation, and it would dispatch a kernel onto the GPU. And as you dispatch more of these kernels, you can see that these kernels are sort of scheduled onto the GPU. This first example actually shows a pretty good case where the GPU is more or less fully utilized through the computation. But often this is not the case. So let's consider the second example where the CPU jobs you're sort of bottlenecked by the CPU. So your GPU is sort of waiting for task assignments from the CPU. They're finishing up their work very, very quickly, and they're just waiting for more jobs from the CPU. So the red sections that you see here are the time the GPU spends not doing useful work. And here you're sort of paying for it, but not getting sort of your money's worth. And so essentially the process of optimization is we want to move more towards the first case where you use your hardware as fully as you can. So how common is this problem? And the answer might surprise you. It's actually quite common. So we did a study at a local ML research institute in Toronto, and we looked at GPU utilization on their compute cluster. And on average, they're only having around 32% utilization. And sort of not to shame anyone, but this presents a lot of opportunities for optimizations. And we believe that people should be better informed of how they could easily improve hardware utilization. We can also sort of speculate why this is happening. Why do we have this low utilization? And this could be because of two reasons. The first is that researchers typically care about model accuracy, so the percentage accuracy you get on the training data, on the testing data set, and not so much about compute efficiency. And the second reason is people always tend to want the better hardware, the more modern GPU for the training workloads, but the workload itself is not properly adapted to the larger compute capacity. So this often leads to the case where the GPU is not really the bottleneck of your computation, but rather the CPU or sort of data transfer. So this is why typically you often see this kind of low utilization. So again, this is the thing we observed in a research cluster. So it's not optimization is not as simple as just hire systems people prior to doing large scale training. The problem of optimization sort of permeates all aspects of the ML operation, beginning with the researchers and the developers. So what does it mean to do performance optimization? And performance optimization typically is sort of an iterative task. People would first identify bottlenecks, then apply training optimizations to address those, and then look at how much benefit that these bottlenecks, solving these bottlenecks gives you. So identifying bottleneck usually involves looking at which resources using these kinds of resources. Typically means deciding where you should make the change and how much of an improvement you can expect. And finally, you will want to look at how much improvements that you get by applying these. And so looking at the existing sort of landscape of deep learning profilers, there are profilers provided by both machine learning frameworks, such as PyTorch and TensorFlow, and hardware vendors, such as NVIDIA and Intel. But we fundamentally don't think that these are very good tools for machine learning developers. And the main reason is that these are mainly geared towards systems engineers, where they're more concerned about, for example, individual operators. Why is this conv2d running so slow, rather than sort of end-to-end model performance? And fundamentally, systems people reason about performance differently from ML practitioners, where in the heads of ML practitioners, it's less so about individual operators, but more about the topology of your model. And we summarize three key issues with these profilers: incorrect granularity, lack of interactivity, and lack of predictive capabilities. And let's go through the first two and then leave the third to the end. So this is a screenshot of PyTorch Profiler. It shows you sort of a timeline trace of what happens during the training. So it shows you sort of down the call stack when each operator runs, and also how long the operator runs for. This is fine if you more or less know what you're looking for, but if you're starting with a model architecture and wonders, where did my time go, it becomes sort of difficult. So you can roughly identify the different parts of your training, the forward, backward, optimizer step. But identifying things at an operator level and relating it to your model topology might be difficult. In the forward pass, you can see that you can see sort of the model hierarchy, but it's very tedious to find the line of code that incurred the cost. And then the backward pass, it's even worse. Backward pass is run by the AutoGrad engine, and everything is sort of, you can see everything is just piled together. Right? You see the order of operators that are backward operators that are running, but you can't really, well, efficiently at least, compare that to your model topology. So this is a case of incorrect granularity where it shows you too much information. It shows you everything all at once. And doesn't present the information in sort of the granularity that you expect as a developer. Here are some more examples of incorrect granularity where people, for example, aggregate things based on operator type. So you look at, in aggregate, conv used this much resources, but that's not fundamentally how machine learning researchers reason. And lack of interactivity is another problem. So reminder that profiling and optimization is very iterative, right? So you want to, once you look at the results, you want to quickly get back to making some changes and improving your performance. But a lot of these tools are either command line based, or you call some kind of profiler API to display results. It doesn't provide a convenient way for you to quickly go back to making changes and then looking at how those changes affects your training throughput. So we present DeepView, which is CentML's open source interactive visual profiler with predictive capabilities designed for ML practitioners. And the goal of DeepView is to present performance information in an intuitive way to ML developers. It not only tells you about performance bottlenecks, but it also gives you energy consumption information, and it even tells you, out of the options, deployment options, which ones will be the most cost effective for you, for your workload. And DeepView runs inside your development environment, so VS Code, but we're looking to support other tools. The sort of front end interacts with a backend that can run anywhere, right? You can either run it on your local machine, some compute cluster that your company owns, or in the cloud. And we also provide this utility to conveniently share resources or results with your coworkers, for example. And we're going to follow this with a demo. So I guess before we begin the demo, are there any questions from the audience? All right. So let's. So in the demo, we're gonna sort of go through a example process of how we can optimize a sample implementation to get a multiple-fold speed up when we do training. And the model we're going to be looking at today is NanoGPT, which is a quite famous open source implementation of a transformer-based language model. It has approximately 6 million parameters. It's a fair bit smaller than some of the production models out there, but this is just to make it fit on our GPU. So let me share my screen. So we have this implementation with us right now, and this is essentially the model. You can see GPD here. And let's analyze this. Let's analyze this model with DeepView. So to start, you have to install the DeepView Explore extension from the marketplace, and also install the backend, the profiling backend from pip. So to begin profiling, all you have to do is open the context menu and select DeepView from the list. And once you do that, it's going to ask you for where your project is. So we're going to tell it that. And then we're going to click on Begin Analysis. And what DeepView is sort of doing now is it runs your model on this cloud instance, and then tells you, like, it measures different aspects. It runs the model multiple times to measure sort of performance variance and how different hyperparameter choices can affect performance. I think I lost connection to the backend. Sorry, just restart. Yeah, so by the way, this is how you would run this backend. It's a Python package. Simply runs that, and then you can connect the front end to it. And while the training, while the profiling is happening, let's take a closer look at this implementation. So in model.py is different PyTorch modules. So this is where you would define your model. And in addition to this, we also have to tell DeepView about our model. So to do that, we have this file called entrypoint.py. So this is, going back to the slides, this contains sort of three functions that you have to declare. You have to declare a model provider, which returns an instance of your model, input provider, which tells DeepView about what your input looks like, what data type it is, and what the shape is. And finally, you also have to tell DeepView about what an iteration looks like. So what this function does is it returns a function that performs one forward and backward pass over here. So taking a look at this interface, we can see quite a lot of things going on here. And I would like to draw your attention first to this sort of vertical bar on the left. So this shows you where time has gone. So hovering over different parts of this graph shows you operations. And furthermore, it shows you what the forward and backward time are. And roughly, you see the backward is roughly twice what the forward is. And you can also double click on one of these, and it will show you where exactly in the code that incurred this cost. And so if we just scroll through this code, you can see that different parts of it are highlighted, and those are the tracked sections of your the sections that are tracked by DeepView. And you can hover over each one of these. So these typically represent operations that you're doing on the GPU. You can see, for example, by the way, the darker it is, the more invoked it is. And you can see the number of invocations, the forward and backward time, and the memory footprint. So the next thing we're going to look at is this sort of memory and throughput view. So what this shows you is what the peak usage, how much GPU memory your model training has been using, what the capacity of your GPU is. We're using a T4 here, so 16 gigabytes, as well as this sort of throughput. So throughput refers to how many samples you can get through each second. This also includes what DeepView thinks your predicted maximum is if you train with a larger batch size, for example. And interestingly, these bars are draggable, so you can drag this up, and it will tell you like what would be the predicted throughput for a particular batch. So the first optimization we're going to look at today is batch size. So we can often optimize, we can also often increase our training throughput by using larger batch size. And that is because data is fed into GPU one batch at a time, and GPU sort of works on that batch and moves on to the next. And if the batch is too small, then we're going to be spending most of our time on communication, and sort of I/O instead of compute would be dominating your compute. So let's use a larger batch size. Let's use, for example, 96. Initially, it was I think like 700 something. So let's see what the throughput would be if we use a larger batch size. And you can see that once we make the change, DeepView has detected our change in the project and prompts us to restart profiling. And I guess while this is going on, I'll ask for questions from the audience, if there are any. Feel free to post them in the chat, and then in between these profiling, I will try to answer them. And oh, I forgot to mention that we will show this later, but if you're doing data parallel training, having a small size not only gives you more overhead in terms of I/O with the GPU, but also overhead like communicating between GPUs. So once we make that change, we can see that the throughput has gone from the initial sort of 700 to more than double. And we can also see that, let's see. Well, I guess I didn't show the model breakdown just now, but let's wait for that to finish. DeepView also shows you like device utilization. So this shows you sort of a hierarchy of your model, so you can see the basic blocks. And if we use a smaller batch size, what this utilization would be is, I think, around like 30-something%. So that means most of your time your GPU is doing is essentially idling. You're wasting, I guess, time and energy by not saturating the GPU with work. And once you increase the batch size to something larger, then now the GPU is spending most of its time doing computation rather than communication with the CPU. And above this sort of breakdown, we can see this message saying we recommend using tensor cores, and that sort of tells us about our second optimization, which is automatic mixed precision. So in modern GPUs, NVIDIA GPUs, there are this thing called tensor cores on the GPU. And what it is essentially is it's a specialized hardware that does matrix multiplication. But it comes with one limitation, that your model must be, your data must be in lower precision, so not FP32, to use this special unit. And it turns out that a lot of our computation doesn't really need to be done in high precision. And you can convert the computation into a lower precision, so FP16, and it not only lowers your arithmetic complexity, but also conserves memory, which could allow you to use a larger batch size. And more importantly, it allows you to use this high-performance tensor core that is available. And PyTorch already has utilities on converting your computation from higher precision to lower precision. And you can do that through the Torch AutoCast API. So let's apply that change and see how it affects our computation. So what I've done now is I have enabled AutoCast by wrapping my model computation inside the AutoCast. So let's wait for this to do its thing. So now we can immediately see an improvement in the throughput. So before it was 1700, now it's much higher at 2400 samples per second. So I guess breakdown takes a little bit of time to complete. But let's see, what's the next one? I guess while we were waiting for this, let's look at another useful feature that DeepView provides, which is called DeepView Predict. So it essentially tells you what the expected training throughput would be of your model on different GPUs, and this will come in handy during the time for deployment. And we're going to talk about deployment once we finish the optimizations. So now we can see that we're like around 20% of the time is spent on executing kernels that utilize the tensor core. So we're actually using this high performance circuit, and that's the fundamental reason why we experience a higher throughput. And so the model breakdown view also allows you to sort of zoom into your model and look at individual operations. And we can see that most of the time is spent on these blocks. So each of these contributes to 12% of total runtime, and there are 8 of them, so that's like 90-something%. And we can zoom into this, and we can see this sort of attention mechanism that is using a significant amount of the block time. And within attention, we can see all of these sort of small operations that have very poor GPU utilization. So if we're going to launch a lot of kernels on the GPU, then we're going to spend a lot of time on, like, for example, kernel launch overhead. So what that really means is we're having the GPUs doing less useful work doing the computation, but more work sort of managing, launching the kernels. And there has been this recent-ish research work called flash attention, which provides a higher performance version of this attention operator, which is the block that you see here. And what it fundamentally does is it merges or fuses all of these operators into a single operator, a fused kernel, that has a much higher performance. And the reason for that is it reduces the overhead of launching all of these small kernels. And to enable this operation, this optimization, we just have to turn an option on. I have a flag set here that enables flash attention. I think this goes down here. During model initialization, we will tell it to use flash attention. So let's see what the throughput would be once we apply this optimization. So we see a more moderate increase in performance. We went from 2400 to 2700, which represents something like a bit over 10%. And I guess we'll wait for the analysis to finish. We can actually also see that transformer now uses a less amount of time than before. And that is mainly because we have optimized the main mechanism for transformer, which is the attention mechanism. So if we were to, so this is the last optimization we'll do today, but if you were to try to optimize model execution, you would probably focus on some of the other bottlenecks that you can explore around here. So after we make the change, we can see that now instead of having all of those small operations, we have this A10 operation called scale dot product attention, which is our fused attention mechanism. So this one. So after we have optimized our model, we started with something like 700 samples per second, and now we're at much higher, 2,700 samples per second. Now suppose that you decide to do a large-scale training or deployment. We can look at these sort of options that we have. So before we talked about DeepView Predict, which tells you the runtime across different GPUs, but DeepView takes this one step further and tells you, suppose that you want to deploy this on one of the cloud instances on GCP, AWS, or Azure, what sort of the cost and time trade-off would be. So let's actually increase the number of iterations because usually the data set is much larger so that the scale becomes more realistic. We can generally see that there's a negative correlation between time and cost. And that is reasonable because the more powerful GPU we get, it's going to cost us more. So here, it really depends on what your bottleneck is. If you have a deadline, say you're submitting a paper, then you probably want to spend a little more on the more powerful GPUs. But if you're not in that rush, then you're able to actually save a lot of money by going through one of the less powerful GPUs. And once we click on one of the instances, it will show you what the provider is, the estimated cost and running time, what the instance type is, as well as sort of this energy view on which data center it is the most energy efficient to deploy to. And I guess for completeness, you can also see what the energy is on your local machine and some convenient equivalences to things that you might be familiar with. What this tool also allows you to do is compare your energy consumption to the other training runs. And typically, more optimized, as we mentioned earlier, more optimized implementations would be more energy efficient. And the reason is, if you're using a GPU, if you're utilizing your GPU more, the power that the GPU consumes might be higher, but you're running them for a lot shorter time. So usually you end up saving energy. And then the thing that powers this sort of prediction across different GPUs, that powers what we see here in this plot, is something called DeepView Predict, which is a very unique feature that we have as part of our toolchain. So what this tool does is, given your model code and a measurement on your local GPU, is able to generate predictions on different destination GPUs through a mixture of scaling and predictive modeling. And from experimentation, this method is a lot more accurate than heuristics, and it also saves you an enormous amount of time compared to evaluating your model training on each of these target GPUs. So this is very useful in informing you about, A, if you're using your GPU to its fullest extent, and B, which target GPUs is the most cost effective. So let's look at two sort of examples that So you might ask, aren't more powerful GPUs better? And again, this is not always the case, especially if your model underutilizes your current GPU. So on the left, you can see an example of convex small with sort of a small input. And you have a large range of GPUs with different sort of performances, right? You have very high-end GPUs such as the A100, and maybe an older one like the T4 or 2080 Ti. You can see that all of these GPUs perform roughly the same. And that's because you're not really using the hardware to its fullest extent. So the performance increase in like the capacity increase doesn't really manifest in training performance. But once you sort of increase the input size, you can see that now using a better GPU does make a difference. The A100 is almost twice as powerful as the T4 at training this model. And the same story can be seen with model sizes. So with the same input size, but different models, you can see that using a large model often allows you to utilize compute capacity better. So using this tool, you can see, is it really beneficial for me to move to a more powerful GPU compared to a slower one? And we currently support all of these GPUs, ranging from older ones to the H100, which is almost the newest generation. We're actively working on supporting more GPUs. And DeepView Predict is very accurate in making its predictions, often with the error being no more than 10%. And against this powers the view, this powers the deployment view, where you can see the time and cost trade-off. And DeepView is currently under active development, and we're constantly introducing new features. And one of the new features that we have recently shipped is the support for data parallel training predictions. So what this does is it takes a measurement of your local machine and makes predictions on what the performance would be if you use data parallel training. So if you trained on multiple GPUs. And so you can see from the plot, this is a screenshot, and you can see the number of GPUs and the estimated training aggregate throughput. And with a small batch size, you can't really get good scaling, right? You get worse performance when you use 2 GPUs because more time is spent on communication rather than computation. But once you use a larger model or larger batch size, then the scaling becomes more normal. So this is able to tell you in advance if your model implementation would scale with different numbers of GPUs. And another sort of new feature that we're planning to ship very soon is this refreshed UI that provides a lot clearer presentation of all of the existing useful features that DeepView provides. And you're welcome to learn more about DeepView at our docs website at docs.centml.ai. We also welcome you to visit our GitHub, and you can find the links to all of those, as well as some quick start guide and basic tutorials on this documentation website. I guess with that, we'll end the talk, and then I will ask for questions from the audience. All right. Thanks a lot, everyone, for coming. And yeah, I guess that concludes the talk.